Hey, welcome to this problem. We have water leaking out of an inverted canonical tank at a rate of 0.0084. Unfortunately, we have it leaking out. It's going out. The rate out is 0.0084 cubic meters per minute are going out of the thing, and water is being pumped in. The rate it's being pumped in, we don't know. Right? It says at the same time that water is being pumped into the tank at a constant rate. The tank has a height of 6 meters, diameter of the top is 4.5. Water level is rising. So water level is going up, so I'm guessing the water coming in must be faster than the water leaking out. When the height of the water is 5 meters, find the rate at which the water is being pumped into the tank. Okay. There's maybe just a little bit harder than the other one. Um, so identify the rate letters. Well, here's the real trick on this one. The We're talking about volume, right? The change in the volume is going to be the rate that water's coming in, being pumped in. This is pumped in, minus the rate that it's being leaked out. Let me let that sink in for a second. Does that make sense? The rate of change of how the volume of water here changes is the rate in minus the rate out. Suppose I said, hey, we're pumping in 100 gallons every minute and leaking out the bottom is 60 gallons every minute. So if you subtract that, that means we're adding 40 gallons every minute to the volume. Does that make sense? The rate in minus the rate out is how the overall volume is changing. So V is one of our rate letters, kind of on the back end, you know? So, and then the other one, if you read carefully, you got to read carefully. It says, what is it? The tank has a high diameter, water level is rising at a rate. There it is, at a rate. The water level is rising. So that's the height of the water. The dH, dt, the change in the water height is point. So it's positive because it's rising. The height is growing. So let's go put that on our diagram. So we have right to there. We have the height of the water. And right here we have the, try to do a little bit better, the radius of the water. Okay, and we know that the overall height, they told us, is 6. And the overall diameter of the top is 4.5. So I just want half of that. So half of 4.5 would be 2.25. See what I did there? I just took 4.5, cut it in half, and put it right there because that's I just want the radius. So okay, back to it. So the height. So there's our rate variables: dH, dt, and dV, dt, which is the change in volume is rate in minus rate out. Okay. So step 2, write an equation that relates V and H only. You got to relate those letters only. So that's we'll start with this. So volume of the cone is 1/3 pi r squared h. Now he has our V has our h, but he also has r. We got to get rid of r. So get rid of r because we don't want any others. V and h only. So how do we do that? We've done this before. It's all about this similar triangle thing. We say um, 6 is to 2.25 as h is to r, right? Because the overall height of the cone is to the overall radius of the cone, like the water cone's height is to the water cone's radius, right? The h to r is h to r. For the overall cone, same ratio for the little water cone. So once we have that, then we can go Okay, diagonal, diagonal. So 6R is 2.25H. Finish solving for R divided by 6. Boom, there we go. So R is that. Plug that in for R right there. Or let me back that up. There we go. Plug that in for R right there. Right there. Because you got to get rid of that R. So then we have V equals 1/3 pi. And then we get to that R. What is R? Let me double too big. 2.25H over 6. Well, I should do that. Let me change the color for clarity. So 2.25H over 6 squared H. See that? I just plugged in, and now I've got a relationship, an equation with V and H only. Let's clean that up a little bit. It's going to be 1/3 pi. I'm going to take these numbers, 2.25 over 6 squared, and then I'm going to have H squared separately and the other H. So one more step of clean up 1/3 pi, 2.25 over 6 squared, and then H cubed, right? Because H squared H is H cubed. Okay, so there's step 2, the big important step. Step 3, d dt, both sides. So once you got that equation that only involves those letters, you're going to go derivative with respect to time, the left side, and the derivative with respect to time, the right side. So what's that going to give us? That's going to give us dv dt equals, and I'm going to put the 1/3 pi, 2.25 over 6 squared stuff there. Okay. And the third power comes down. Subtract 1 from the power, a squared, and then dh dt. Okay. So now we can, step 4 is plug in the numbers. Remember, you don't plug in the numbers until after the derivative. Because plug them in early, the derivative of just plain old numbers is going to be 0. All right, so what do we got? The height of the water is 5. So the height, so that's going to go right here. That's the height of the water, not the height of the overall cone, but the height of the water. And dH dt told me somewhere there it is 0.17. dH dt 0.17. The water level is rising 0.17. So this is 0.17. Okay, so we get dV dt equals. So I'm going to hit the buttons on Desmos now. So, oh, here, let's do this. Let's just cancel this 3 and this 1/3. They're just going to make 1. 3 over 3 is 1. So I'm going to put that in Desmos. Pi 2.25 over 6 squared. Pi 2.5 over 6 squared. So pi times 6 squared. Pi 2.25 over 6 squared. Let's go back. So I'm looking right here. Pi 2.25 over 6 squared. 5 squared times 0.17. 5 squared times 0.17. 5 squared times 0.17. Okay, 1.87759. 1.87759. 1.87759. Okay, now here's where I pull a trick. What is dV dt? Well, remember up above we observed that dV dt is rate in minus rate out, right? That's how you track a change in the total volume of water in the cone. How fast the water's coming in minus how fast it's going out. That's the change of volume in the cone, change of the water volume. So rate in minus rate out. So I'm going, oh, so this is going to be rate in minus rate out. And specifically, I know the rate out. They told me. The rate out is 0.0084, right? It's leaking out 0.0084. So that's 0.0084. So now we can solve for the rate in. by adding 0.084 to both sides. So radian equals. So I'm going to take that answer I got from Desmos and add 0.0084. That answer from Desmos and add 0.0084. And there we go, 1.88599. 1.88599. Is that the real answer? There it is. So that was a little bit tricky, wasn't it? Right there at the end, right? We had to say, well, the dV/dt is rate in minus rate out. We know the rate out. Add that over. There we go. And so we're able to solve right at the end for that problem. And so there we go.